Okay, so I wanted to talk about some applications of the laws of sines and cosines and how we can use those to solve problems involving vectors. Now, if you remember, a vector is just a quantity that has a direction and a magnitude, and we represent that with an arrow. So the direction the arrow points is going to be representing the direction of the vector, and the length of the vector will represent the magnitude. So that can be things like velocity, acceleration, force, or even displacement of how far something's gone in a particular direction. So today what we're looking at is a problem with an airplane. And so we have a plane is flying at a heading of north 35 degrees west, which just means that from due north, we've turned 35 degrees towards the west. And that's our heading. And then there's a crosswind of 15 miles per hour due west. It says the plane flies at 250 miles per hour in still air, so we want to know how fast it's going with the wind. So here we're going to have two vectors. One's going to represent the plane on its own, and one's going to represent the wind on its own. When we add those two vectors together, we're going to get the resultant, which is going to be how fast the plane goes with the wind. So because we're going to be able to do this with the law of sines or cosines, and we're not going to be worrying about being too accurate with our drawing, but you do need to be close. So the first thing I would do is just go ahead and draw a quick north-south line on your paper. It's going to give us a direction to measure from. So when our plane is flying north 35 degrees west, that means towards the west, we're going to be measuring a 35-degree angle. And so that would be 35 degrees right there. And we'll represent the length of this vector, 250, as the speed of the plane. Now that's not the only vector we've got in this problem. We've also got to include the wind. And so the wind is going due west. It's going to be a much smaller vector because the wind's only 15 miles per hour. And so we've got our situation represented there. Now, one thing we do know, due west and due north, those are going to be perpendicular to each other. So we're going to have to use that fact to find some of these angles when we make this vector problem. Now, the resultant vector goes from the beginning of the first one to the end of the second one. And so we'll represent with this purple vector, and we'll call it C. A, B, and C. Now, the whole point of these is we have a triangle. We can use the laws of sines and cosines to figure out everything about this triangle because we know the directions of the vectors and we know their lengths. We have these two sides here, and we want to find the third side. So what we really need is this angle in the middle. Because if we have the angle in the middle, we can use the law of cosines to solve for C. So to find that angle in the middle, we have to just think about the relationships between these two vectors. If I had another north-south line here, and I kept this vector going, that would be 35 degrees. But I would know that these two angles here would add up to 90. So that would tell me that this angle in this side is 55. And then I can use this linear pair, 55, and with this angle would add up to 180. So I can subtract from 180, and I know my angle in here is going to be 125 degrees. So it's all about those applications of, those would be corresponding angles. A lot of times we'll be using alternate interior angles to figure out what direction you're going to be going in. So now that we have two sides and the angle in between, that SAS condition, we can find our third side by using the law of cosines. So we're going to have C squared equals 15 squared plus 250 squared minus 2 times 15 times 250 times the cosine of 125. Ran into my problem there. But all we have to do is punch that into our calculator. 15 squared plus 250 squared minus 2 times 15 times 250 times the cosine of 125 degrees. And I get that C squared is going to equal 67,026, or about that. And then we just take the square root. And C is going to be 258.9. And since that's representing our magnitude of our vector, that's miles per hour. That's the speed of our plane. Now, in order to find the direction, let's say we wanted to find the direction the plane was going, in that case, we always want to measure our angles from due north. So in this case, we need that whole angle from there to there. We already have part of it. We know there's 35. So what we need to find out is this part here. We can call that maybe a y. So we need to find out this y angle. Just this little tiny part here and add it to the 35 to get our total answer. Well, this is where the law of sines can come in. We know this 125-degree angle, and we just found our opposite side of 258.9. We have the 15, and we want to find the y. So we can use our law of sines. The sine of 125 degrees divided by the opposite side, which is 258.9, is going to equal the sine of the angle we don't know over the opposite side, 15. To solve this, it's simply a matter of cross multiplying. 15 times the sine of 125 equals 258.